Hello, everyone, and welcome to today's 1W-MINDS seminar. We're lucky to hear from Mark Transtrum from BYU. Mark is an associate professor of physics and astronomy here at Brigham Young University in Provo. He utilizes techniques from statistical physics, information theory, control, and machine learning to work at the nexus of physical modeling, applied mathematics, and data science. His research is funded by the NSF, DoD, DOE, and NIH. And today we're lucky to hear from him talking about eGAD. Double descent is explained by the generalizing aliasing decomposition. Turn it over to you, Mark.
Thanks, Kevin. Thank you for the invitation. Happy to be here. And thank you all for coming, quote unquote, virtually to listen. I'm going to talk today about the title that Kevin just read. The preprint is available on Archive. So if you're interested, this place to look. And I want to make sure I recognize co-authors who helped with this. I think Gus worked very hard to figure out how to put eGAD into the title. And he's here today, so shout out to him. Um, but a lot of the work that I do is very interdisciplinary, and uh, while thinking about this phenomenon of double descent that we famously see in a lot of data science applications, neural networks are perhaps the most famous. But while thinking about some other areas of mathematics, we were thinking about relationships between concepts and signal processing, specifically aliasing and overfitting in more traditional data science problems, and that's kind of where this came about. And so I'm going to introduce a novel decomposition, sort of in opposition to the bias variance decomposition that we're most familiar with. So let's see if I can get this to advance. So the way I'm going to go through this talk, the first section will be kind of a problem statement where in data science we're interested in making inferences from samples, and the standard paradigm for thinking about model complexity in that space is the bias variance decomposition, where we're balancing two sources of error, bias and variance, to find a classical sweet spot. But modern machine learning and the modern regime exhibits some interesting behaviors, such as double descent, that are a little harder to understand in terms of bias variance, at least intuitively. Perhaps the math still holds, but the intuitive explanations that we get for these risk curves aren't so clear. But in fact, I will try to argue that these phenomena that we see in machine learning are just one case of a much broader phenomenon. So here's an example of a risk curve that comes from a material science application in materials discovery. And I'll talk a little bit more about the details of where this comes from. But the point is, this is a complicated curve. And it's not just looking for a classical sweet spot with a small model and balance and comparing it against a modern machine learning regime where empirical risk gets small. There's lots of ups and downs in between. And explaining this curve in terms of bias variance is also kind of tricky. And so then I'm going to set that aside for a moment. We'll do a little introduction to signals processing. I'm going to talk about Fourier series and the phenomenon of aliasing, which is where different signals can be mistaken for one another because of finite sampling effects. And then I'm going to try to tie all of this together by introducing what we call the generalized aliasing decomposition, or the GAD. And so we'll introduce the GAD, which explains these risk curves in terms of three different components that we call the modeling insufficiency, data insufficiency, and aliasing, which is where the name comes from. And we'll use these to explain some of these risk curves, including double descent, but also some of these more complicated risk curves that come from structured scientific applications, such as the one in material science that I just showed you. And then I'll conclude with some final thoughts about what I think this means for how we think about modeling, model complexity, and data science and machine learning in general. Okay. So with that broad overview of what I hope to get through today, let's talk about inference from samples. So This first bit, I'm going to be a bit didactic, and I apologize, but I'm going to go quickly since this is probably straightforward. But I want to take the time to make sure we get terms and concept. We're on the same page in terms of terminology and concepts. So when I teach regression to our physics students, I usually start with an example such as this. We want to model, okay, population versus time. So this is U.S. Census data. Uh, and I have here two regression fits, a linear fit in black and a quadratic fit in blue, and you can see the fits for what they are. Um, the natural way to think about this is, well, if one is good and two is better, why not go to extremes? And so the first thing you have students do is, well, let's fit these to increasingly higher order polynomials. And here we have 11, 12 data points, so you can go up to an 11th order polynomial and fit things exactly. And this was a lot of fun to teach during COVID because the predictions for the models that you get predict complete population collapse in 2020. Um, Here we are on the other side of COVID, and that thankfully didn't completely come to pass. But there's clearly a disconnect between the quality of the fit and the quality of the prediction. And this is the message we give students. But there's actually a little bit more going on here. If you start looking at details, here we're doing least squares regression, and you could implement least squares regression on the computer in a few different ways. So in the table here, I'm showing the prediction. Oh shoot, I forgot now what I'm plotting. I think I'm predicting prediction in 2020 actually, using different algorithms for implementing least squares regression. So you could just call uh, least squares. You could actually call the pseudo inverse function, or you can actually implement what should be the formal definition of the Moore-Penrose pseudo inverse. And they generally agree until you get up into this regime where you have higher order polynomials that are making crazy predictions. Actually, the predictions very depend quite strongly also on other details such as the choice of algorithms, things that nominally should be doing the same thing formally on pen and paper do different things under the hood on the computer. So a few takeaways that we like our students to understand after going through this exercise is the best predictor is not necessarily the one that has the best fit to the observations, and that the quality and credibility of those predictions depend on uh, critical ways often on many of the details, such as the model class. Are you using lines or quadratics? But they can also depend on things like which data did you choose to fit? How was the function sampled? Here, we're dealing with census populations, so it's every decade. But so we didn't have a lot of choice. In a lot of science and engineering applications, there's a sensor placement problem, which is where do you collect data? And that ends up being an important part of the data fitting problem as well. And then there's the algorithm that you choose to actually solve the problem. Do you use the pseudo inverse? Do you call the least squares out a function directly? Things like this, and they can also make a difference. And so when this gets generalized to machine learning, do you use SGD or Atom? Those sort of details play a big role in the quality of the predictions, even if the actual fits to the data themselves look identical. Um, and so the thing that we're often concerned about is this problem that overly complex models can respond very strongly to the minutia or the noise of the specific samples. And in this case, there was a population dip around 19. Well, it wasn't really a dip, but the model overpredicts population in 1940. 1940 population was less than what you would have naively guessed. And of course, there were major world events in the decade before that. So maybe that's not so unusual, but we're generally okay with not predicting that dip in 1940 because you don't expect to predict things like the next Great Depression or when World War III is going to happen just by looking at population data. So we are, as data scientists, we're okay with not fitting things perfectly because of noise that's outside of the predictive capabilities of the data that's available to us. And so if you go to the extreme and fit things with an 11th order polynomial, you'll get a very complex model that latches onto these details that really aren't signal, they're noise. And so, and consequently, the model swings wildly between the samples, and we don't like self models. The paradigm that we always use to understand this is the bias variance trade-off. So the way I is a combination of signal, deterministic signal F plus noise C. And the thing that you want to minimize is the mean squared error, for example, some sort of error function, in this case, mean squared error, which is the difference between the actual data and your estimator. Okay? And the bias variance decomposition tells you that you can decompose this error into three contributions: bias, variance, and irreducible error. So in terms of mean squared error versus model complexity, irreducible error is just what it is. It's constant. But the utility of this comes in that the other two terms have very predictable dependence on model complexity. So bias is large for small models, models with low complexity, few parameters, and generally decreases as you make the model more complex. On the other hand, the variance increases. And so if the sum then is the total is the sum of all of these, what you really care about is finding the sweet spot in the middle where things are balanced. So there's a systematic trade-off between bias and variance. And as we think about how complex a model do I need to have, this is what we have in our mind as we're balancing that, is this trade-off. So overly simple models have large bias. Bias dominated errors are underfitting. Variance dominated models are overfitting. And the unquestioned dogma in the field is that we want to find this sweet spot that balances these two competing effects. A model of sufficient complexity to capture the signal without being too dependent on the noise. Okay. Now, in modern data science and machine learning regime, where we often have very, very large models, one of the surprising effects that we see is that radically over-parameterized models, such as very large neural networks, can have very good predictive performance. And this has been termed, this phenomenon has been termed double descent in the literature, because in the picture that I just drew, you have this trade-off between bias and variance in the classical sweet spot. But once you reach the point where you have as many parameters as data, well, now you can fit the data perfectly. And what we seem to observe is that when you go into this modern regime where you have more parameters than data, the mean squared error on predictions actually decreases rather than continues to grow. And this was surprising to much of the community. There needs to be a few things said about this phenomenon. First of all, when you're out here in the modern regime where you have more parameters than data points, there isn't a unique solution to your learning problem. The function you're trying to minimize no longer has a unique minimizer. In fact, the thing that interesting about the interpolation threshold, that's the point where you have just enough parameters to fit the data perfectly. Beyond this, now there's a whole family, there's a null space of solutions that fit the observation or the training data perfectly. And so part of what's going on here is you have a choice among many candidate solutions that are all equally good in terms of the training data. And so out here, part of what's going on is that you can leverage this choice and choose, for example, a minimal norm solution. And doing that seems to lead to better predictive performance. So a picture that I'll often draw is something like this, and I apologize, the legend's a little bit large here. Is suppose you're trying to fit data that's drawn from this black curve, and so the data points are in red, and it's a very wiggly, noisy signal, so it's hard to fit. The classical sweet spot would be something like the blue curve that kind of roughly interpolates. It doesn't capture every wiggle, but it kind of goes through the center and roughly tracks the black curve. That would be the classical sweet spot. At the interpolation threshold, you exactly fit every red data point, but it comes at the cost of these wild swings that go off the scale of the axes in between. And then what happens is you go beyond that into this modern regime. You can now pick solutions that oscillate even more. So you can have more ups and downs in your solution, but the amplitudes of those oscillations get smaller. And so they become statistically more similar to the oscillations in your true function. And so you have more wiggles, but since they're compressed, they're statistically similar to the true signal that you're trying to capture. Okay. And that seems to be phenomenologically what's happening here in this modern regime. But coming back to the intuition imbued by the bias variance trade-off, it all kind of goes out the window here in this modern regime. What made bias variance so useful is that bias was this monotonically decreasing function. Variance was a monotonically increasing function, and you just wanted to balance the two. And so it was kind of tuning a slider until there's some was minimized. Um, as a mathematical statement, bias variance still holds out here in the modern regime. But the intuition that variance is going to continue to grow, that's what's breaking down. And so it's the intuition that seems to not be so useful for thinking about these models. Now, a big part of the theme that I want to communicate in this talk is that this is just one example where bias variance ends up not being a very useful paradigm for thinking about model complexity. And there's actually a few of these, a few other examples. One of these I've spent much of my career thinking about a class of models called sloppy models. These are also uh, extremely over-parameterized models, but they end up being very inflexible in terms of their learning capacity. And so if you measured complexity just naively in terms of number of parameters, bias variance gives you very much the wrong intuition. There's a theory for this. It's based on information geometry that these models exhibit low effective dimensionality, which is even though they're massively over-parameterized, in terms of their statistical properties, they act as though they are much simpler. And once you understand that, then you can develop theories for how to reason about model complexity for these models. But the point is, bias variance really gives you the wrong intuition if you apply them to sloppy models. And another example where bias variance is misleading are highly structured data that come from science and engineering applications. So here's an example of a loss curve that comes from a cluster expansion model, which is a very commonly used model in materials discovery. And the x-axis, we have number of parameters. The vertical axis is predictive performance, and the interpolation threshold, the naive interpolation threshold, where there's as many parameters as data points, doesn't appear to play any role. And way even to the left of the interpolation threshold, what should be the classical statistical regime where bias variance ought to be applicable by all standard statistical theory, isn't able to explain these ups and downs that you see in the curve if you assume that bias and variance are monotonically decreasing and increasing respectively. And so these are cases where that intuition that guides practical data science for tuning model complexity just break down if you just naively apply them to these problems. Okay, so that's the state of affairs from the modeling data science side. Now I want to take a bit of a detour. We'll stick a pin in that idea for a moment. I'm going to talk about signal processing and Fourier analysis. So again, I'm going to, for those familiar with signal processing, this might be a bit pedantic, but let's take a few minutes just to make sure we're all on the same page in terms of terminology. So in signal processing, we think of functions. F of t might equal something, and it's a rule that maps time points t into some values f of t. And a big part of the theory in signal processing is that functions can be represented in multiple ways. So one expression might be f of t is some, fill in the dots on the right-hand side, whatever your functional form is for your expression in terms of time. But you can also represent these in terms of series. So the most common approach that we teach our students are Taylor series. You can expand the series in terms of polynomials, and then rather than expressing the function or the signal by giving a rule that is in terms of t, you can just specify the coefficients of the series. Connecting this back to our data science formulation, the coefficients of the series are going to be analogous to our parameters, and then the polynomials are the basis functions. The series representation that we're really interested in here is Fourier series, which instead of a polynomial expansion, we're going to do an expansion in terms of sines and cosines or complex exponentials. So, and the picture, a common picture that we would draw to teach students about this is something like approximating a square wave with a sum of these sines and cosines. You can see through the series here. As you add more and more terms, you get better and better approximations. Okay, so the idea is that we can represent the signal or the function by giving you the Fourier coefficients instead of the rule of how we evaluate things in time. And this ends up being incredibly useful in lots of applications. So, for example, in acoustics, where I have many collaborators, you measure pressure at a microphone as a function of time. There's your signal, but there's a lot of physical insights that can be gained by converting it to a Fourier representation and looking at the contribution of the signal from different Fourier components. Okay. So we can switch between representations, and different representations imbue us with different physical insights into the nature of the signal. Now, Fourier ends up having lots of variations depending on the domain. So you have a Fourier series on a finite domain. If you extend the domain to be infinite, it becomes a Fourier transform. So you have integrals instead of sums. Or you can make the domain discrete, which case we call a DFT, discrete Fourier transform. And then the sums get truncated at a finite value instead of being an infinite series. And consequently, there's all sorts of nuance between the time domain, the time domain and the frequency domain. You know, if you have an infinite range of time, it ends up mapping nicely into an infinite frequency domain. But if in the Fourier series case, if there's a finite time, you get discrete but infinite number of frequencies in your Fourier reconstruction. Or if you just have a finite number of discrete time points, then you end up with a finite number of discrete frequencies. Okay, so there's some nuance here in how the representations map to one another, but we can represent these signals in different ways, even if the domains appear to be different. Okay, now where this connects to data science is that in signal processing, we ask the question, when can you reconstruct the Fourier representation? And reconstructing the Fourier representation is really the same as reconstructing the entire signal. It's the same thing from only a finite number of samples, which sounds like a data science problem. And the theorem that undergirds much the thinking along this line is the Nyquist-Shannon sampling theorem, which tells you that if you have a function f of t, and you know that its Fourier representation has no frequencies higher than b hertz, then the signal is completely determined by its values at a sequence of points spaced less than 1/2b seconds apart. Okay, so conceptually what this means is if you know that your signal is band limited, that means that all the high frequency components in your Fourier series are zero. That means there's only a finite number of frequencies, non-zero frequencies, that you have to reconstruct. And so if you have sufficiently informative samples, that's what the spacing has to do, is making them sufficiently informative. If you have sufficiently informative samples and you have enough of them, then you can reconstruct the remaining non-zero Fourier terms from these samples. And so I'm going to shamelessly steal a GIF from Wikipedia, where if you have such a Fourier, such a signal that's band limited, so the figure on the right shows the Fourier representation, and the frequency components go to zero outside of some range, then on the left you see the reconstruction. As the reconstruction gets more and more points, at some point you'll reach a critical value where suddenly you match it exactly, and adding additional points does not improve the reconstruction of the signal. You have enough to get all of the frequencies, and any additional uh, um, uh, samples just carry redundant information. Okay. Motivated by this Nyquist-Shannon sampling theorem, we want to calculate the first n Fourier components from n uniform samples, assuming that the higher order Fourier components are zero. And you can write down from the Fourier analysis, you can write down the formulas for what these reconstructed Fourier components should be. And then once you have the Fourier components, you can reconstruct or interpolate the full signal by just assuming that there's no high frequency component. So all I've done is taken the finite samples, and I've now extended t to be continuous to interpolate between the samples. And the fast Fourier transform is the algorithm that solved this problem way, way back in the 60s. This was a very important problem to solve. And back then, we were really limited in computing resources. And so you wanted to make sure you didn't have too many multiplications or too many memory requirements. And so this was an immensely powerful algorithm at the time. It's actually a family of divide and conquer algorithms that allows you to efficiently construct these Fourier samples, these Fourier coefficients from samples. And this fast Fourier transform is really the workhorse of modern signal processing. In fact, at the turn of the 20th century, Siam made a list of the most important algorithms of the 20th century, and this was among them. And so influential, when I talk to my colleagues in acoustics or electrical engineering who do signal processing regularly, they will often just casually in conversation refer to any type of Fourier transform, whether it's algorithmic, discrete, continuous, as an FFT. It's just become such a common parlance in that field that's because it's been so influential. Now, what happens though if your signal doesn't actually satisfy the Nyquist sampling theorem? What if it's not band limited? Well, if the contributions, the high frequency contributions to the signal are known to be zero, then the signal is said to be band limited. And there's a particular sampling rate called the Nyquist frequency, where if you sample at such and such a rate, that's related to the fastest frequency in your signal, then you are said to satisfy the Nyquist condition. So if your sampling satisfies the Nyquist condition for a particular band limited signal, then you can reconstruct your signal exactly from finite samples. But if there actually are contributions from the higher order frequencies, then a phenomenon emerges that's known as aliasing. And the idea with aliasing is that your reconstruction of your signal is distorted because you've incorrectly assumed that some contributions are zero when they're actually non-zero. And so you will take there will be high frequency contributions to your signal that you will mistake for low frequency contributions because you have incorrectly assumed that they're non-zero. So the picture that we draw is something like this. If you sample at the red points, then each of the three signals that I've shown you here are identical at those samples. And so we would say these high frequency signals are aliased into the low frequency sampling. And so the FFT would reconstruct the thick black line, even if the true signal was one of the other two. And that's the phenomenon of aliasing. And now I'm not sure if this is going to work over Zoom because I'm going to show some animations. Hopefully this comes through, but there's lots of fun illustrations of this that we often use in the classroom. Here's one where as the disk is spinning, visually what appears to be happening is different layers of the disk look like they're going forward or backwards at different speeds. That's due to the aliasing of the frequency of the spinning disk and the spacing of the black and white stripes with your visual refresh rate. And so you get similar things with camera refresh rate. So there's this famous phenomenon called the wagon wheel effect, where the spokes of the wagon wheel appear to be stationary because their spinning is at the same frequency as the camera refresh rate. And then there's other fun examples that you can give where if the shutter speed of the camera is synced with the rotor speed of the helicopter appears to just float up without spinning, because the high frequency true speed of the rotor is aliased into the constant contribution of the Fourier mode. Okay, so with that in mind, I'm going to combine these two themes together to introduce what's the main theme of the talk, which is this decomposition that we call the generalized aliasing decomposition. And it's going to help us think about ways that unmodeled components of our signal get mistaken by our models, and then consequently help us reason about model complexity or choice of model complexity in data science. Okay, so hopefully at this point it's clear that the signal reconstruction problem from signal processing is fundamentally a data science problem. Given a finite number of samples of the signal, such as the population, we want to reconstruct the full signal. Now, data science in particular, the intuition that comes from the bias variance trade-off suggests that the optimal model size is at this sweet spot. That's the trade-off between the bias and the variance, which isn't at the interpolation threshold. It's some simpler model. But the fast Fourier transform that I just introduced, if you think of it as a data science problem, is operating exactly at the interpolation threshold, right at the point where data science intuition suggests that we should be wildly overfitting. And yet the FFT doesn't really come with a lot of caveats about be careful where you use it. We regularly use it all the time, also on noisy data, on signals that aren't technically band limited, and we use it to draw meaningful physical insights, even though we're operating right at this interpolation regime where classical data science tells us we ought to be getting nonsense. And so we have a few examples where bias variance seems to be misguiding us. So there's the modern regime of double descent, where it's really unclear how to reason about what happens to bias and variance out here for over-parameterized models. There's these highly structured science and engineering problems, and fast Fourier transforms, which I'm proposing to you to include in your list of examples of anomalous generalization, where we get good inference here at this point, this interpolation threshold point, that where we ought to be suspicious about results. Yet we cavalierly use it all the time and get good results. Okay. So how are we going to think about this? The standard ansatz that we used in statistical regression, this was the basis for deriving the bias variance trade-off, is that the data Y is decomposed as signal plus noise, and where noise here is some random variable. Usually we assume it's Gaussian distributed if we're doing regression. Okay. Well, I'm going to propose that we start from a different ansatz, and it's an ansatz motivated by signal processing. So first of all, let's think of Y as a signal. It's a vector of data, potentially an infinite dimensional vector of data. And we're going to partition it into training and prediction. So I've done that with these two subspaces. So Y of t, Y sub t is going to correspond to our sample points at which we're going to do our learning, and then we're going to predict on white people. We're thinking of the full signal as a single vector that we partition into this direct sum. Okay. And I say we're going to think of data as samples from a more general signal. I need to be careful about terms here. Here I mean signal as in signal processing. This isn't signal as in signal and noise. This is our samples from a signal processing type of signal. Okay. And then we're going to break that up into training samples and all the other predictions we might care to make. Validation set, if you will. Then we're going to further decompose the signal as the sum of the modeled and unmodeled modes. So this is like the low frequency Fourier components, and these are the high frequency Fourier components that we're going to assume are zero. But we're going to keep in mind, even though we're going to assume they're zero, we're going to keep in mind that they really are there so that we can reason about whether we should be including them, whether any individual term should be included in the unmodeled or the modeled piece. Okay. And if you assume a linear model, then these two ansatz together become this nice block partition. So our full model is a linear function of parameters, but we're going to break the full model up into training and prediction, and we're going to break the full representation up into the modeled and the unmodeled. And so our modeling matrix gets this block representation. So this is the contributions to the training predictions on the modeled subspace, the training predictions on the unmodeled subspace, the predicted part of the signal on the modeled subspace, predicted part of the signal from the unmodeled subspace. Okay. So that's the key ansatz that we're going to use to derive this decomposition. But let's take a minute and think about this and how it compares to the standard approach. So in particular, if we're just doing the training, looking at the training subspace, the standard statistical ansatz would be you have Y is a design matrix times parameters plus noise. This is the standard picture. And all I'm doing really is saying I'm going to replace the noise with things that I'm calling unmodeled signal. And so superficially, these look very, very similar. All I'm doing is labeling the C as something else. But there are some subtle differences. When you formulate the standard statistical ansatz, you always assume that the noise is a random variable. So, see, but in a lot of cases, actually, C isn't random. I put random in quotes. This is a sticky question. What do you mean by random? And maybe that's part of the problem. But quite often, the error in our model is just that we haven't captured some small deterministic part of the signal. Um, so this way of thinking about it allows us the flexibility to think perhaps more precisely how to think about modeled components or unmodeled components when we're trying to reconstruct the deterministic signal from uh, uh, from finite samples. But we really aren't restricting ourselves to that. If there really is truly random bits in the signal, then the parameters just become random. But notice that the randomness in that case is encoded in the parameters, not in the noise term itself. And so there's some nuances here in this ansatz that I'm proposing. And I'm calling these out because I think these nuances are important for helping us reason about model complexity. And I'm going to try to convince you that this decomposition here actually gives us some useful insights into understanding what's going on in these regimes where bias and variance intuition kind of breaks down. In particular, what I'm going to be thinking about is what happens when I move a mode out of the unmodeled subspace into the model subspace. So we're going to move the partition between modeled and unmodeled down a row and move and explicitly model something. And reasoning about that transition is much more natural, I argue, in this ansatz than in the traditional ansatz. In particular, it's really hard to reason about things like how does the irreducible error vary with model class in the traditional ansatz, and that becomes much more natural in this case. One of the other advantages of this decomposition is that it's label independent. What do I mean by that? Well, the labels are the y values that are over here on the left. The decomposition itself is all over here on the right. So we can do analyses in terms of this decomposition, in terms of this matrix, without knowing anything about the labels. And that's going to be important for things like experimental design, model selection, before you've seen any data. And that ends up also being a powerful application here. Now, there are some downsides to thinking about the model this way. In particular, you need to anticipate how you're going to extend your model into the unmodeled modes. In the case of Fourier, it's kind of natural. You add higher order frequencies, but in a lot of applications, it's not so obvious how this extension should happen. So it does require you to think hard about these things. But if the question you're asking is model complexity, you kind of already have a continuum or a set of choices you're thinking about. And so if that's already your question, I would argue you're already addressing this issue. Okay, so now we're going to learn parameters from data. So the modeling assumption is that the unmodeled modes are zero. And when we're training, we can't see them. So what we really think we're solving is that the training points are just equal to this MTM theta m. So MTM is equivalent to the classical design matrix in linear regression. Now, we're going to estimate the model modes, the estimated parameters with some pseudo inverse. So our inferred parameters are just going to be the inferred model parameters and then zero for the unmodeled ones, where the modeled parameters are just some pseudo inverse times the samples. And the choice of pseudo inverse here is really a surrogate for your choice of learning algorithm. And all the results that we do, we're going to assume that it's the Moore-Penrose pseudo inverse. But future work might explore other options. And now we ask, after we've done this reconstruction, how sensitive was our learning algorithm to the unmodeled modes that may have existed? And this is exactly analogous to the aliasing question in signal processing. If you know that there are some maybe small high frequency terms, how does that impact your reconstruction of your Fourier signal? Okay, so to do this, we're now going to recall that our true signal is really the combination of some true modeled terms plus some unmodeled terms, and the explicitly include these unmodeled modes in our expression for this. Okay, so in other words, how distorted is our learned representation? So what we can do is take our expression for the true signal and plug it into this expression and get something. So at this point, all I've done is a substitution, and the expressions are starting to look a little bit messy, but we can do the algebra and we can carry the terms around. But the important thing to recognize is that because we have this term now that is the contribution from the unmodeled modes, this is the effect the unmodeled modes have on distorting our learned representation. And I'm going to call this generalized aliasing. This is the generalization of the Fourier effect, where unmodeled terms distort your learned representation. Okay. Now we can look at terms in this representation, try to make sense of what they mean individually. So our full signal is reconstructed signal is just our matrix times our inferred parameters. And again, now we plug all these in and it gets increasingly messy. But notice that because we're doing everything in the linear regime, we can do some analyses. The reconstructed signal is linear in the true parameters. And that means that the error is also going to be linear in the true parameters, right? Because the true signal is linear in the true parameters, the reconstructed signal is linear in the true parameters, so we can plug all of these in and factor things out. And so the error is going to be equal to this matrix that quantifies how the inferred parameters have been distorted multiplied by the true parameters. So this matrix is going to be important to our analysis. I'm going to call that E sub theta. It's the matrix that tells us how the how the true parameters through the learning process are distorted to give us errors. And so finally, this means that our error is linear in the true signal, and so we can write the error term something like this. There's the full modeling matrix M and its inverse with this term in the middle that depends explicitly on the partition between the modeled and the unmodeled. So this decomposition is one of our primary results. And now with this, we can start thinking about what are the potential sources of large errors in a modeling framework. So if we look at this expression for the error, it's the norm of this term. And so that means it's bounded by the product of the norms of each of the components. If we look at these, well, the norm of y, that's largely determined by the units of y. In practice, we're probably interested in relative errors, so that term doesn't matter so much anyway. Those two terms are just the condition number of m, the norm of m times the norm of its inverse. And that has nothing to do with the choice of the partition between modeled and unmodeled. So if we're worried about how error changes as we change the complexity of our model, the only non-trivial contributions can come from this error matrix that I've introduced. So the argument is that really all salient features of generalization curves can be explained by understanding how the contributions to this error matrix vary with model class and with the choice of sampling. And because it's block diagonal, it gives us a natural way of decomposing terms into three different parts, the non-zero terms. So in particular, the upper left, we call the data insufficiency error. I'm going to denote it as P sub n because if you notice the expression, it turns out this is a projection operator that projects into the null space of MTM. MTM is the classical design matrix. So it's the null space of this design matrix is the extent to which the data is insufficient to constrain the predictions. The lower right block we call the model insufficiency because it's just the error introduced by the unmodeled components. And then the off diagonal term is the generalized aliasing operator that I've talked about a bit before. I'm going to denote that by A. And so we have three terms in our error matrix. We can understand these geometrically something as follows. So let's say this three-dimensional space is our parameter space. And so we have some signal, and it should be represented by some point in this space. And I'm going to draw, in order to help with the perspective, these lines are the projections onto each of the faces of this three-dimensional space. Now, we're going to partition the space into modeled and unmodeled. So let's say these two axes are the modeled parameters, and the axis coming out of the board is the unmodeled parameters. Then when we do our parameter inference, we're going to end up with some different parameters that are different from the true representation. So this error is what this matrix is going to help us reason about. So of the three terms, we can understand how they relate here. First of all, the model insufficiency, the red, is proportional to the unmodeled component. So it's just projecting the full signal into the modeled plane by moving through the unmodeled subspace. Then we have an aliasing contribution that's going to distort us somewhere else. The formula for the aliasing, recall, is this MTM inverse MTU. And that means that the output of the aliasing operator has to be in the range of MTM inverse. So if this is the range of MTM inverse, the aliasing operator has to be parallel to that subspace. And then finally, we have the green contribution, which is our data insufficiency. And that's going to move us in another direction. Remember, it's the projection onto the null space of MTM, which, if you recall your linear algebra, is the orthogonal complement to the range of MTM inverse. And so it has to be parallel to this line. And it has the effect of, this is the part where the minimal norm solution comes in. We're essentially moving along this line in a way to pick out the minimal norm solution and excuse me. And that's just the choice we're making because the data is insufficient to otherwise constrain the parameters. Okay, so we can understand the contribution geometrically from each of these three terms. A couple comments. The two insufficiency operators are bounded because they're basically projection operators. On the other hand, the aliasing has no obvious bounds, and so that's going to be the source of interesting non-generalization curves in general. And with that, let's actually look at some results and compare these with real generalization curves. So here are demonstrations of double descent for a couple random feature models. So the first RF are random ReLU features and RFF are random Fourier features, and we're fitting these to the MNIST data set. The black curve is the actual empirical risk. So notice here at the interpolation threshold, there's a peak. Likewise, that's a little more dramatic for the Fourier features. The other curves show contributions from the aliasing, or from the generalized aliasing decomposition. So blue is the aliasing, P or green data insufficiency, and red is the model insufficiency. And you can see how they break down. Because the green and the red are projection operators, they're kind of boring, and they don't do anything too interesting. But notice the peak in the at the interpolation threshold that gives rise to the non-monotonic double descent behavior really appears to correlate with the peak in the aliasing operator. And the dashed line is the norm of the aliasing operator on its own, indicating that you can actually predict where this will occur before you've seen any of the labels in the data. Here are a few other examples, also random feature models on different data sets. In the interest of time, I think I'm going to not say too much about features here. We'll just move forward. But there appear to be some consistent patterns in the behavior of these terms. And you can actually show theoretically that these different contributions have to have certain dependencies on the model complexity. So in particular, the data insufficiency has to be a non-decreasing function of the parameters. Because it's a projection, as you add more terms, the kernel of MTM can only get bigger. So data insufficiency can't decrease. Model insufficiency is a non-increasing function of the parameters. As you add more parameters to your model, the dimensionality of the unmodeled subspace gets smaller, and so model insufficiency cannot increase. But aliasing can be much more interesting. It can either increase or decrease depending on how the model is updated. And in particular, it seems to be driven primarily by the norm of the inverse part of the learning algorithm. So there's a theorem in the paper that says when changing the model by moving one column of M from the unmodeled to the modeled subspaces, the two contributions to aliasing, MTU never increases, but MTM inverse, it cannot decrease if the column is linearly independent of the other columns, and it cannot increase if the column is linearly dependent on the other columns. So that gives us a rule to reason intuitively about where non-monotonic behavior is coming from. And in fact, if we think about the generic case where we're just adding, say, random features to our model, you get a picture that looks something like this. In the classical regime, well, the model insufficiency is just going to decrease. The data insufficiency is generically 0 in the classical regime because the design matrix has full column rank. And the aliasing will just increase monotonically because if you're adding random terms, each column is going to be linearly independent of the previous ones. But then once you hit the modern regime, things turn around. The model insufficiency still decreases. Data insufficiency now starts to grow because you're over-parameterized and you don't have enough data to constrain the model. But the aliasing is now decreasing because now every column that you add is linearly dependent with the column that with the ones that existed because you already had enough columns to span the training space. And so this is the classical picture of double descent and how the generalized aliasing decomposition explains all the primary features. Okay. But what about Fourier aliasing? Remember, what motivated all of this is fast Fourier transforms seem to operate at the interpolation threshold where things ought to be crazy. What's going on? Well, we can go through this analysis for the Fourier case. So if you assume uniformly spaced points, we're going to introduce omega as an nth unity. Then the design matrix is some variant of a Vandermonde matrix. But because this omega n is an nth root of unity, you have this identity that omega n to the ln power equals 1 for all integers of L. And that means that this term NTU is just going to be multiple copies of the design matrix. And so the aliasing operator, which hits this MTU with the MTM inverse, is just going to give you multiple copies of the identity. And that means the norm of this operator isn't very big. It's just the spectral norm is 1. So unlike the other examples we were just looking at, where the aliasing operator had this large peak at the interpolation threshold, classical Fourier aliasing, the aliasing operator is actually quite well behaved. And so this is giving us some insight into why fast Fourier transforms are so useful. The aliasing effect is bounded here in ways it's not bounded for more classical data science problems. There are other examples where similar effects happen. Let's see, I think I'm getting low on time, so I'm going to just go through this quickly and say that if you formulate a collocation algorithm for solving a differential equation, you get something that's very similar, that looks like a regression problem. You have a bunch of constraints that are the conditions of the differential equation that you need to satisfy at a bunch of points, and you need to choose basis functions so that the error in the differential equation is minimized throughout the rest of the domain. It's just a data science modeling problem. If you do an example, say just a simple solve u double prime of x is equal to some source term, you can calculate the aliasing decomposition, and you get a decomposition that looks something like this. If you use a sign basis function with 32 uniformly spaced collocation points. Notice that what happens here, the optimal model size is again right at the interpolation threshold. That's where the error is smallest. And in fact, the aliasing is nearly constant. And that's because we've really just reconstructed Fourier aliasing all over again. The errors are dominated by the model and data insufficiency on either side. And so in the small regime or the over-parameterized regime, the optimal really is at the interpolation threshold. And so, as I said, this is equivalent to Fourier aliasing. But this is yet another example where the intuition from the bias variance trade-off leads us astray, that here we really want to be at the interpolation threshold, but it's only because the effects of aliasing are bounded. They're not very large. Okay, so in fact, uniform collocation points are provably optimal for the Fourier basis, precisely because they minimize aliasing. And you can see this by explicitly taking the previous example and perturbing the location. So instead of having the collocation points be uniformly located, you perturb them a bit. And sure enough, what happens is the aliasing effect grows, and you start to see a double descent in the collocation clusters. So that's where the cluster expansion term comes from. So by clusters, I mean things like pairwise interactions, so nearest neighbor interactions, next nearest neighbor interactions. But you can also include three-body interactions, four-body interactions. If you're familiar with an Ising model, this is like a generalized Ising. And this is a really interesting problem from a data science perspective because the data and the structures, the clusters and the crystalline arrangements that you look at are highly structured. And it leads to very non-trivial generalization curves. But we can conduct a generalized aliasing decomposition. And sure enough, when we do this, we find the norm of the aliasing operator here in blue tracks nicely the peaks in all uh, of our generalization curve for the aliasing of the cluster expansion. Here at the top, we have a little indicator that indicates when the next basis function is added, whether it was linearly dependent or independent of the previous terms. And you can see that just as the theory predicts, when you start adding linearly dependent terms, you get decreases while independent terms lead to increases. And you can explain, in fact, predict nicely what the generalization curve looks like before you've seen any data. So you can use this to do experimental design, model design before data collection and before sampling. Okay. And you can produce the classical double descent curve just by, instead of taking the order, the physically inspired order that I call natural order, by shuffling the order of all the terms, it now looks like a random feature model, and you get the double descent phenomenon. Okay, so let me conclude with some final thoughts. I think the key takeaway that I'd like to emphasize here is the distinction between the starting points of our analyses. That in the classical bias variance trade-off, you start with signal plus noise. And I've suggested maybe sometimes we like to think of a different partition. We want to think of modeled, unmodeled, observed, and unobserved, which leads to this generalized aliasing decomposition. And these are just different ansatz that reflect two fundamentally nuanced different ways of thinking about modeling, with each with respective advantages and disadvantages. And hopefully I've shown you that there are perhaps some advantages for thinking about modeling in these terms. So to summarize, modern data science exhibits there's a lot of non-trivial phenomena that can occur in these generalization curves, such as double descent. But classical analysis problems from signal processing or collocation methods for solving differential equations are also at odds with some of the intuition that we get from bias variance trade-off or modern data science theory. And so we've introduced this generalized aliasing decomposition that provides insights into these generalized risk curves, both through classical and modern regimes. And it also explains the lack of overfitting in some other domains, while being applicable to highly structured data that often arises in science and engineering applications, such as material discovery. We're just starting to think about this. So there's a lot of open questions. I've done all of this using linear algebra. What happens when you go to the nonlinear case, such as neural networks? Does all of this depend on the choice of algorithm, atom versus stochastic gradient descent versus more Penrose pseudo-inverse? What happens if the signals are non-deterministic and you incorporate distributions over your choice over your observed signals? All of these are things that are yet to be explored, but we found this very insightful on our end for thinking about model complexity in a lot of practical applications, and hopefully you've found it interesting. Kevin, I apologize. I think I've taken the whole hour, but if anybody, I'm happy to answer questions if we have time if people want to.
Awesome. Thank you, Mark. We'll stop the recording.